Here's a real-life data set. In this data set, we have the 100 U.S. senators who are in office right now. I collected and entered all this data myself. Up here we have the names of the variables, and in here we have all of the data values. Don't worry about this column over here. This is just a column in which I'm keeping track of people's names. Let's see what we have over here. I think we have one other column besides gender. No, these are just the person ID numbers. As we look through this data set, we might have certain questions that we'd like to answer. For example, we might wonder, have older senators been in office longer? Is there a tendency for the older senators to have been in office longer? And we might have another question. We might wonder, do senators who have been to more colleges tend to have more degrees? So as the number of years of college goes up, does the number of degrees, as the number of colleges attended goes up, do the number of degrees earned go up along with it? We might also wonder, when people have been in office longer, does that mean that they have fewer years left before their term expires? The questions that we're asking right now are questions about correlations. And a correlation can be positive or negative. A positive correlation is something in which people who are higher on one thing tend to also be higher on something else. And it makes sense for older senators to have been in office longer, or at least that should usually be true. So it makes sense for there to be a positive correlation between age and years in office. A negative correlation is something in which people who are higher on one thing tend to be lower on something else. For example, senators who have been in office longer should usually have fewer years left before their term expires. So that's probably a negative correlation. And one way to look at whether two variables have a positive correlation or a negative correlation in your data set is by making a graph called a scatterplot. And I'll show you how to make that with Excel. If we're interested in age and years before, if we're interested in age and years in office, we would highlight these two columns of data. If we press Control, we can highlight the other column, even though the two columns aren't next to each other. We go up here to where it says Insert, and then we go to Scatter, and then we go right here to the icon at the top left. What we have here is a graph in which each person is one of these diamonds. Sometimes when you make a scatter plot, you use dots, but Excel uses diamonds. What this is right here is one person, or one of the senators, who's, it looks like, about a little bit older than 40, and they've been in office for about 11 years, because I think what Excel did is it put years in office down here, and it put age up here. We have an x-axis and a y-axis. I think it put years in office on the x-axis and it put age on the y-axis because that would be the only thing that would make sense based on how this data looks. So what we need to do is we need to look at this person and go down to the x-axis, and we find out the number of years that person has been in office, and it looks like about 12. If we go over to the y-axis, we find out how old that person is, and it looks like maybe 41 or 42. If we look at this person up here, at this line, they're exactly 80 years old on the y-axis, and it looks like maybe they've been in office for about 37 years or 38 years if we go straight down. So what we can see here is that there's a pattern in which people, senators who are older up here, tend to have been in office longer, because when you look at the younger senators down here, a lot of them haven't been in office very long. Like if you look at the people in their 40s, pretty much all of them are down here between 0 and 12 years in office. We don't really have anyone in their 40s who's been in office longer than maybe 12 years. When we look at people in their 50s, we start to go up a little bit further, because this person has been in office maybe 18 years. And then when we go up to people in their 60s, we start to see people who have been in office even longer. We're starting to go up here to maybe 20 years in office. And once we get up to people in their 70s, we start to see people who have been in office for a very long time. So older senators tend to have been in office longer, and there some people who were stacked above each other, like these two people, because it is possible for two people with different ages to have been in office at the same time, because not everyone starts as a senator at the exact same age. So this person, it looks like, became a senator when they were maybe in their early 30s, and this person, and now they're about 12 years later, they're in their early 40s. This person right here maybe became a senator in his or her early 40s, and now about 12 years later, that person is in his or her early 50s. So not everyone starts at the same age. So you can have these people who are stacked above each other, like these two people, who are at different ages but have been in office the same number of years. But still, overall, we see a positive correlation in which there's a tendency for older senators to have been in office longer. The dots have this overall rising pattern from left to right. And if we click here on one of the dots and drag down, we can click on Add Trend Line. And this adds a line that summarizes the correlation that we see. We have this overall rising pattern from left to right, which is a positive correlation. It would also make sense for there to be a positive correlation between number of colleges attended and number of degrees earned. People who go to more colleges tend to earn more degrees. So let's see what this positive correlation looks like. We can see if it's even a positive correlation after all. Sometimes even if something makes sense to be a certain type of correlation, it turns out to not be true after all. So we have to look to see what the data shows. The reason why it might not be positive after all is because it could be that people who have attended a lot of colleges have dropped out of a lot of colleges, and they don't earn very many degrees. So in order for us to find out whether senators who have gone to more colleges really do tend to earn more degrees. We have to look at the data. We have to look at what the data shows. So let's see what we have here. It looks like we only have a small positive. It looks like we have kind of a weak positive correlation because the dots do seem to be rising up here like this, but it doesn't look very consistent because we have people who were spread out vertically pretty far. It's not nicely following a line from left to right like this. So there's a difference between a stronger positive correlation and a weaker positive correlation. If the dots are far away from the line and they're not following the line very well, it's a weaker positive correlation. If we had dots like here, 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 and here, and they're all pretty close to the line, that would be a strong positive correlation. For example, if you were looking at the number of miles that a person drives per week and the amount of money that the person spends on gas, we would probably see a strong positive correlation in which the people who are driving more miles per week are spending more money on gas, and it would be much more consistent, and it would be a stronger positive. Because if we were looking at number of miles driven per week down here and amount of money spent on gas up here, you wouldn't really have someone up here. You would probably definitely not have someone up here who isn't driving very many miles and is spending a lot of money on gas, unless they were buying gas for a different person. And you also wouldn't have a person in this corner area down here who is driving lots of miles per week and is spending very little on gas. That's why I'm saying it would be a stronger positive correlation in which the dots would follow the line more closely. But in this case, we have something where there's more people who were exceptions to the pattern. And you might be wondering why there's so few dots in here. The reason is because there's actually a lot of people stacked at this place right here. We have a lot of people who have, looks like 1 degree, maybe, and have attended 3 colleges. I'm not actually sure which one is on which axis, but we have a lot of people who were stacked right here, and a lot of people who were stacked right here. Let's look at something else. I said that there should be something here that would be more of a negative correlation. Oh, if you've been in office longer, you should have less time left in office. So that should be a negative correlation. You can look at the scatter plot to see what it looks like. And it actually looks like I don't really see much of a correlation here. When you have this type of a shape, it's considered to be no correlation. When you have this kind of blob or rectangular shape, it doesn't rise or fall from left to right. Let's see if it really isn't no correlation. We can get our trend line that summarizes the correlation. It actually does look like it's a little bit negative. meaning there's a small tendency for people who have been in office longer to have less time left in office. But it doesn't look very consistent. For example, here we have someone who's been in office, looks like almost 40 years, and they have 5 years left. But here we have someone who's been in office 10 years, and they only have 1 year left. So it's a negative correlation, but there are a lot of exceptions in here. It's not something where the dots are following the line really closely. If we were looking at something like number of missed credit card payments and people's credit scores, we would see more of a stronger negative correlation, because people who miss more payments have lower credit scores pretty consistently. So you probably wouldn't have someone way up here who has missed a lot of payments and still has a very good credit score. And you wouldn't see someone down here who has missed very few payments and for some reason has a very low credit or poor credit score. I'm not completely sure how credit scores work, but I think that it would be pretty consistent and that the dots would follow a dropping line pretty consistently if we looked at number of missed payments and credit score. That would be more of a stronger negative correlation, and this is more of a weak negative correlation. If the dots are far away from the line, like they are here, it's a weak negative. Also, if the line is, like I said, if the line is rising, it's a positive correlation. If the line is dropping, it's a negative correlation. Let's look at this website right here. We can actually plug in dots for people's data values, and it actually tells us what type of correlation we're seeing. This is more of a strong positive, like we might see with number of miles driven per week and amount spent on gas. When we add in dots that are further from the line, like this, it becomes a weaker negative. And if I add in some up here, it eventually becomes no correlation, because the dots aren't, overall the dots aren't rising or falling from left to right. If the dots are perfectly lined up on the line, it's a perfect positive correlation. This might be something like age and the total number of birthdays a person has celebrated in their lifetime. When a person's age goes up by 1, they've always had 1 more birthday during their lifetime. That would be a perfect positive. If the dots are perfectly lined up on a dropping line, it's a perfect negative correlation. If you looked at the number of hours that people are awake per day and the number of hours that they're asleep per day, when a person has been awake, when a person is awake 1 more hour per day, they're always asleep 1 fewer hour per day. When hours awake goes up by 1, hours asleep always goes down by 1, and it's a perfect negative. But most things aren't perfect. This is a fairly strong positive, but when we add in dots further away, it becomes a weaker positive, and then it becomes no correlation when it becomes a blob or a rectangle. When the line becomes completely flat, it's no correlation. This line is just summarizing the correlation. Here we have a fairly strong negative, but if we add in dots further from the line, it becomes a weaker negative. The pattern is still dropping from left to right overall, but it's expanding. It's like you're blowing up a balloon, and it's getting wider. There's actually a value called a correlation coefficient. It can be calculated to tell you how strong a correlation is. The correlation coefficient goes from -1 to +1. 0 is no correlation. When you go up closer to 1, when you go further from 0 and up closer to 1, you get more of a stronger positive. And once you get to 1, it's a perfect positive. It can't go any higher. When you go from 0, or no correlation, down closer to -1, you get more of a strong negative. And eventually it lines up on a straight line and becomes a perfect negative. There's also a button here where we can throw out the data and get a new sample. You can see that no correlation doesn't always mean one type of shape. There's actually a variety of shapes that all have no correlation, but what they all have in common is they're all pretty much blob shapes that aren't rising or falling from left to right. These are different examples of no correlation. We could calculate the correlation coefficients with some of our examples. For example, let's do it for years in office and years before term expires. We can do equals CORREL, we do parentheses, we highlight this column, we put a comma in here, then we highlight our other column right here. Close the parentheses and click enter. And it's only the correlation between years in office and years before term expires is only -0.25. That's a pretty weak negative correlation. And we saw it in the Scatterplot that it was a pretty weak negative correlation. If we go back to our website right here, we can see that a -0.25 we can see the -0.25 is about right here. This is what we were seeing with our correlation between years in office and years before term expires. What about the correlation between age and years in office? We just need to find an empty box right here. We type equals CORREL. We highlight age. We click on a comma. We enter a comma, and then we highlight years in office. And what Excel is doing is it's plugging all of these values into a certain type of formula to calculate a correlation coefficient. And the correlation coefficient shows how strong the correlation is, and it also shows if it's positive or negative. We got a 0.67, which is a pretty decent positive correlation. That's somewhere up here. So that it is a fairly decent or a fairly consistent correlation between age and years in office, which makes sense. What else do we look at? We looked at colleges attended and number of degrees earned. Comes out to 0.57, which is more of a medium positive correlation. Both of these are pretty similar, but it looks like this one over here is a little bit stronger than this one over here. So the correlation between age and years in office is a little bit stronger than the correlation between number of colleges attended and number of degrees earned. This one is a stronger positive correlation, and this one is a little bit of a weaker positive correlation. This one might be a little bit weaker because when people go to more colleges, they might drop out of some of those colleges and they don't always earn more degrees, which probably makes this a little bit of a weaker correlation. Let's see where 0.57 would be. We go down a little bit. It's about right there. And 0.67 was about up here. So they are pretty similar. This one is a little bit stronger.